In this lecture, we're going to discuss the correlation. We'll start with an overview of what a correlation actually is. We'll follow that up with a discussion of the assumptions underlying a correlation from a statistical perspective. We'll move on to talking about statistical significance, follow that up with the sign and magnitude of correlations, and then finish up by talking about effect size and practical significance in the context of correlations. Now, starting with that overview, there are different ways that we can describe the association between two variables, and this will depend on the type of measurement scales of each of the variables. So we can describe the association between variables in different ways. So if we have two nominal or categorical variables, we can use what's called a chi-square test of independence to look at that association. If we have a nominal or categorical predictor variable and an interval or ratio, or in other words, continuous outcome variable, we can use an independent samples t-test, an analysis of variance, or even a regression analysis. Now, if we have two interval and/or ratio continuous variables, we can use correlation or regression analyses to look at the association between those two variables. Now, there's different types of correlations, and today we'll focus on the Pearson product moment correlation, but there's also what's called, for example, the Spearman correlation. So if you have two ordinal variables and you want to understand the association between those, you would use that. But today we're going to focus on the association, the strength, and the sign of the relationship between two variables that are on an interval and ratio measurement scale, or in other words, are continuous in nature. And so instead of using the word Pearson product moment correlation again and again and again, we'll just refer to this type of correlation for this lecture as a correlation moving forward. So let's talk about the statistical assumptions underlying a correlation. So what assumptions need to be met to even run a correlation? Well, here are the assumptions that we'd like to focus on. First, cases, which in our case, in human resource management, we're often interested in data about employees or people. The cases are randomly sampled from an underlying population such that the variable scores for one case are independent of the variable score for another case. So this is important to consider in the context of correlation, and this is the first assumption we want to make. Now, randomly sampling people might not always be the way we go about doing things, but we want to at least make sure that there's no really obvious clustering in the data, or in other words, nesting of the data where there's different pockets of people that are more similar to each other with similar scores than other people. Okay? The next assumption is that each variable shows a univariate normal distribution. We also want to make sure each variable is free of outliers or extreme values. We also want to make sure that the variables demonstrate what we refer to as a bivariate normal distribution. So if you break that down, bivariate, so bi, two, variate, variable. So we're talking about two variable normal distribution, and I'll show you how you can diagnose that in a moment. And then we also want to make sure we meet the assumption that the association between the variables is linear. A Pearson product moment correlation assesses a linear relationship between two relatively continuous variables. So let's start with that assumption of univariate normal distribution. So each variable by itself should show more or less a univariate normal distribution. And so we can use things like the histogram in order to visualize that. So here we have the first variable, variable x, and we can see that the frequency of scores from 1 to 5 for this variable seem to follow what looks like a normal distribution. So if variable x looks similar and we see that bell shape there, well, we can say that we've probably met that first assumption. Now, what about that assumption of having no outliers? Well, this means that we don't have any extreme values, and that's what outliers really are. And we want to assess that for each of the variables. And the box plot, or the box and whiskers plot as it's sometimes called, is a good way to do that. And so here's an example where we see beyond the whiskers to the right of the box plot that we see two values that seem to be flagged as being extremes or outliers. And so these would be two candidates for a potential removal here. And there's another reason we might remove these two is that these can actually kind of sway the distribution and skew the distribution and pull your mean actually in one direction or the other. So we want to eliminate any outliers, but we want to make sure we have good justification for doing so, because sometimes these outliers are actually important cases. Sometimes they're just errors in data entry too, so this is a good way to make sure that everything's within bounds. For instance, we just saw a second ago that this variable, let's say variable x, ranges from a low of 1 and a high to 5. Well, maybe it's something weird where someone entered the data incorrectly and actually these outliers represent the value of 6 and 7 respectively. Well, that'd be a data entry error. Let's kick that out or figure out if we can find the correct responses or values for those people. Okay, so we want to make sure there's no outliers. The next assumption we need to meet in order to run a Pearson product moment correlation is we need to meet the assumption of bivariate normal distribution. And this means that we're talking about the distribution that's shared between both variables, variable x and variable y. And so the scatter plot can be a good way to visualize this. So a scatter plot is going to be more or less in the shape of an ellipse when you've met the assumption of a bivariate normal distribution. And there tends to be, as you can see here, greater density in terms of scores in the center of this distribution, this ellipse, than in the outer rings of this. So this would be very typical of a bivariate normal distribution. Now the next assumption has to do with linearity. So a Pearson product moment correlation is designed to assess the linear relationship between two variables, not a curvilinear or non-linear relationship. And so here you can see, based on this scatter plot between variables x and y, that there seems to be a positive upward linear trend here. Okay? And you can see, if you imagine a line of best fit superimposed here, we can imagine this being more or less linear. Now this is where we'd run into trouble, and we'd violate that assumption of linearity if we saw something nonlinear in this scatter plot. You're likely not going to see something as clear as this when it comes to nonlinear relationships, but this is just to illustrate the point here. So a nonlinear relationship has a functional form with curvature, and a Pearson product moment correlation was not going to be appropriate for describing this association. There's other types of tools and analyses we can use if we're interested in looking at curvilinear relationships. But here you can see, if we superimpose that dotted line there, that we do see that curvature. A straight line would not be appropriate here. Okay, so now let's move on to the idea of statistical significance in the context of a correlation. So let's, for the sake of explanation here, talk about null hypothesis significance testing when it comes to correlation. So using null hypothesis significance testing, we would interpret a p-value that is less than 0.05, or whatever 2 or 1-tailed alpha level that we actually set for our p-value cutoff. So using that null hypothesis significance testing, we would interpret a p-value that is less than 0.05 to meet the standard of statistical significance, which means that we would reject the null hypothesis that the correlation is equal to 0. In other words, we would conclude that that correlation is significantly different than 0. Now, if the p-value associated with the correlation coefficient is equal to or greater than 0.05, or whatever value we set that alpha level to, then we fail to reject the null hypothesis that the correlation is equal to 0. In other words, we assume that there's no association or relationship between these two variables based on that statistical test. Now, in addition, we can look at the confidence interval, and specifically if we're interested in an alpha of 0.05, we'd look at the 95% confidence interval, and if that does not include 0, then we can conclude that we meet the standard for statistical significance. If it does include 0, then it would be the same thing as saying we failed to reject the null hypothesis, and we have not met that standard for statistical significance. So here's some examples we can work through in terms of recognizing what statistical significance means in the context of a correlation. So let's assume, for the sake here, which is fairly customary in social sciences and in particular human resource management, that we're dealing with a 2-tailed alpha of 0.05. What that means is that the p-value needs to be less than 0.05 to be treated as statistically significant, or in other words, to reject the null hypothesis that the correlation is not different from 0. So let's look at the first one, where we see r is equal to negative 0.32 with a p-value of 0.02. So the little r italicized is typically how we communicate a correlation for short, the correlation coefficient. So we would say that the correlation value is negative 0.32 and the p-value is 0.02. That p-value is less than 0.05, so we would reject the null hypothesis that that the correlation is equal to 0, and therefore we conclude that this correlation is statistically different from 0. In other words, we can treat the correlation of negative 0.32 as being statistically significant. Now, moving on to the next one, we see that the correlation value is negative 0.09, and we see the corresponding p-value is 0.68. Well, 0.68 is equal to or greater than 0.05, and therefore we would conclude that this is not statistically significantly different from 0. In other words, we would say that we failed to reject the null hypothesis that this correlation is equal to 0. Okay, so now let's talk about sign and magnitude in the context of correlation. And so by sign, I'm referring to the fact that a correlation can take on the value of positive or negative. So this tells us the direction of that linear relationship when we're talking about a Pearson product moment correlation. And so here you can see with this scatter plot, this is illustrating a positive correlation. Hopefully you can see that relationship between variable x and variable y shows more or less an upward linear trend here, so a positive relationship. As values are higher in x, y values tend to get higher too. Now, here's a negative sign example here. Here we can see that as values for x get higher, values for y tend to get lower. And so this is an example of a negative or an inverse relationship between two variables. So again, positive and negative refers to the sign. This is what's really cool about a correlation coefficient. Not only does it communicate how strong an association is, but it also communicates the sign or the direction of that relationship as well. Let's move on to the magnitude of a correlation, which really refers to the size or how big that correlation actually is. And you need to remember that this is magnitude in terms of absolute value. So you can have a really large positive and a really large negative correlation. Okay, so ignore whether it's a positive or negative value, instead just focus on the value itself, independent of the minus or the positive sign. So it's at this point important to note that a Pearson product moment correlation can range from -1 to 1 in terms of magnitude, where -1 would be a perfectly negative or inverse linear relationship, and a 1 correlation would indicate a perfect positive linear relationship. 0 means that there's no association. So if you see a correlation of 0, it means that the two variables do not covary with one another. So let's start with some examples here to really visualize what this looks like. So here's some more scatter plots. So here the magnitude of this correlation, let's say, is -1.0. So this means that there is a perfect negative or inverse association between variables x and variable y. So as variable x increases, variable y decreases in lockstep, or vice versa. So here we see a negative correlation, but here the magnitude is less. So instead of being -1, this is -0.67. So it's still a strong negative association, but it's not a perfect association as we saw a moment ago. Then here's an example of a correlation where the magnitude is 0. As you can see here, there's really no direction to this. There's no systematic pattern in the relationship that we can discern. This would be the typical type of scatter plot you'd see for a relationship or a correlation of 0, meaning there's no magnitude, no association between variable x and variable y. So now let's look at the other side of things. So let's talk about positive relationships here. So here's a strong positive association between variable x and variable y. So as variable x increases, there's a tendency for variable y to increase as well. Now, here's a perfect positive association between variable x and variable y. So as variable x increases, variable y increases in lockstep. So there's a perfect association here. If you were to draw that line of best fit, all of the points would fall on the line here. So this would be represented by a correlation of, let's say, 1.00. We don't need to put the plus sign in front of the 1, as that is implied because there is no negative sign in front of it. Now, if you have time, I highly recommend that you check out this correlation simulator on this great website, rpsychologist.com. And so this tool, this is just a screenshot right here. If you go to this website, what you'll see is that you can actually play around with randomly simulated data in terms of trying to understand visually in a scatter plot what do different correlations, whether positive or negative in sign or strong or weak in magnitude, look like. And it also includes the variance explained. And so variance explained is computed by simply taking the correlation value itself and multiplying it by itself, or squaring it, in other words. And so here you can see in this an example, if the correlation is -0.24, if we square -0.24, we would get about 5.8%. And so this is when we want to talk about the percent of overlap or the shared variability between two variables, we can square the correlation value to get that percentage of shared variance. Okay? So it's important to remember, though, that a correlation by itself, that -2.4, should not be interpreted as a percentage of anything. You would have to square that value in order to get to that shared variance, or that R-squared value. Okay, so we've talked about statistical significance as well as magnitude and sign. Let's now talk about effect size and practical significance in the context of a correlation. So for standardized statistics like a correlation coefficient, we can compare the magnitude of one correlation to another correlation, and the reason we can do this is because a correlation coefficient communicates an effect size. So to quote an article on what an effect size actually is, it's an index of the quantitative relationship between variables. So it's something we can use to compare different correlations across different samples or populations. And so what this allows us to do is to start talking about correlations that are statistically significant in qualitative terms. So it's important, you want to avoid interpreting the effect size, generally speaking at least, you want to avoid interpreting the effect size and or the practical significance if a correlation coefficient is not statistically significant. So if you find that the relationship between two variables, as evidenced by a correlation, is not statistically significant based on the p-value, well, then you would just treat that association as being zero, a correlation of zero. There's no association or relationship there. Now, if you do find a statistically significant relationship, then it's time to start interpreting, well, how big of a relationship, how meaningful or how practically significant is that relationship? And that's where effect sizes come in. Fortunately, the correlation coefficient is already an effect size metric. So in 1992, Cohen offered some guidance and some rules of thumb when it comes to actually assessing and describing qualitatively the magnitude or the size of the effects when it comes to correlation coefficients. Now, it's important that these are meant to be just general suggestions and that you should really come up with your own organization in the specific context. What is considered a meaningfully large correlation versus a small correlation based on whatever it is that you are using the correlation to assess the association between. Now, ignoring all that, it is generally used that a small correlation is around 0.10 when you're dealing with human data. And so that's plus or minus, or that's the absolute value of 0.10. So if your correlation is about 0.10, you can probably say with some confidence that's a small effect, assuming it was statistically significant. Now, if the correlation was around 0.3 or so, plus or minus, in terms of the sign of the correlation, that would mean that's about a medium effect. Now, if it's 0.5, so plus 0.5 in terms of a positive correlation, or negative 0.5 for a negative correlation, we would say that that is a large correlation when we're dealing with human data. Now, we get pretty excited in the social sciences and human resource management if we find a correlation of 0.5 or higher. That's considered quite large. Notice that's by no means a perfect correlation. But when you're talking about human beings and two things co-varying with each other, two variables, that's pretty good. So again, small, 0.1, medium, 0.3, large, 0.5. And these are ways you can describe the size of the effects and determine how meaningful potentially those effects actually are. So this comes into play especially in instances where maybe you find a statistically significant association between two variables based on your correlation and this corresponding p-value, yet you find a very small effect that might be 0.10 or lower. Well, that's going to maybe give you room for pause, because is that something that you would actually want to act upon in a real organization? Is that going to be meaningful if you're trying to change something in the organization? So for instance, if you find a correlation between job satisfaction and job performance, and theoretically you believe that job satisfaction is causing higher job performance amongst those employees, and you only find a correlation, albeit statistically significant, of 0.05, well, that's not that big of a relationship there. And so in terms of gearing towards increasing job satisfaction to improve job performance, it might not be the best approach. Now, if you find a really large effect between those two, well, that might give you some confidence that, hey, yeah, we need to figure out what are the drivers of job satisfaction here, so that through job satisfaction, we can hopefully try to increase job performance amongst those employees. So let's walk through a few examples of what practical significance looks like here. And so we're going to assume that these correlation values are statistically significant, and you can see that evidenced by the p-values here, being less than 0.05. So let's start with the first one. So we see the correlation, or R, is equal to negative 0.32. Well, if you look at this, using that rule of thumb from the last slide we just looked at, Cohen's rule of thumb, we would say that this is a negative and medium in magnitude relationship here. So the effect size, or the effect, is medium by those standards, so we're describing them qualitatively. Now let's look at the next one here. This is a positive correlation of 0.59, and again, the p-value of 0.01 is less than 0.05, our conventional cutoff for statistical significance. And here we would say that this is a positive and large in magnitude effect here, okay? So let's have you try this now. So let's walk through a few examples, and what I'd like you to do here is, after I show these correlations, take a moment and try to think through, maybe even pause this video and try to describe the correlation. We'll assume that these are statistically significant, but you'll now need to describe in practical terms what these correlations mean in terms of the size, or the magnitude and the sign, as well as qualitatively how big or small these correlations actually are. And try to explain them in a way that a general person on the street can understand, as well as someone who's more statistically inclined might understand. So let's start with the first one here. The two variables are age, measured in years, where higher values mean higher years, and happiness, measured on a scale or rated on a scale of 1, which is low happiness, and 5 is high happiness. Here the correlation, let's assume it's statistically significantly different from 0, is 0.28. So how would you describe this relationship here? So take a moment, maybe pause the video and think about that. Okay, so here's how I would describe this relationship. So if I were talking to an audience of people that understood statistics, I might say something like, there's a positive and statistically significant relationship between age and happiness that is medium in magnitude. So 0.28 is pretty close to that cutoff of 0.30, or that conventional standard, that rule of thumb of 0.30 according to Cohen in terms of effect size. So we'd say that's pretty close. Now, if I were going to describe this to someone on the street, I might put it in more conversational terms. I might say something like, there's this tendency that as people get older, they tend to get happier. Or this tendency that as people who are older tend to be happier to a moderate extent. And that moderate extent is referencing back to the fact that this is a medium correlation here, a medium effect size that we're seeing. Now let's do one more example here. So here we're looking at the correlation between organizational commitment, which is rated with 1 equals low and 5 equals higher, so higher values mean higher commitment, and turnover intentions, where 1 equals low and 5 equals high, where higher levels mean people are more inclined or feel greater intention to leave the organization or to quit. So here we see a correlation of negative 0.15. Let's assume this is statistically significant. So how would you describe this relationship, both to someone who has statistical knowledge as well as to someone who you would meet on the street perhaps that doesn't have necessarily that statistical know-how? Okay, so after you've had a chance to think about that, now let me give you a chance, and let me describe how I would tell someone about this correlation if I were to meet them, if they were a statistician versus if they were someone that I met that I wasn't sure if they had any statistical background or knowledge. Well, I would say first that we see evidence of a small or a weak negative correlation between organizational commitment and turnover intentions, such that higher levels of organizational commitment tend to be associated with lower levels of turnover intentions. Now, if I were meeting someone on the street who I wasn't sure necessarily if they had a background in this or understood statistics, I might say something like, people who tend to be more committed to their organization have a slight tendency to feel less inclined to quit their organization, at least according to the data here. So you can see that there's ways that you can practice talking about this, and this is where you really need to know in terms of storytelling who your audience is, so you can describe these findings to them in a meaningful way. But you really do want to both convey that there is a relationship and then the size and the magnitude of that relationship as well, assuming it's statistically significant. So just to wrap up, we talked about in this lecture about what a correlation coefficient actually is as an indicator of the strength and the sign of an association between two variables. And specifically, we've been talking about the Pearson product moment correlation that we've just been calling the correlation for short. We also talked about the statistical assumptions that need to be met in order to run a Pearson product moment correlation. We talked about statistical significance in the context of correlations, as well as sign and magnitude in order to describe the correlations. We finished up just now talking about effect sizes and practical significance as well. So this wraps up the lecture on correlation.